Dear learners, in this unit we will discuss number systems, representation of numeric and alphanumeric expressions in number systems, conversions from one number system to another number system, basics of Boolean algebra, Boolean expressions, precedence and associativity of logical operators, truth tables of Boolean expressions, logical operations and their physical representation as logical gates. Dear learners, after completing this unit, you should be able to understand number systems, represent numeric and alphanumeric expressions in number systems, convert a whole and fractional number from one number system to another number system, solve Boolean expressions, understand precedence and associativity of logical operators, create truth tables, solve and interpret truth tables, and understand the purpose of logical gates. Dear learners, number systems are used to represent numeric values in different ways. The four number systems are decimal, binary, octal, and hexadecimal number system. The first and most commonly used number system is decimal number system. It consists of 10 symbols or digits. The total number of symbols in a number system is known as the base of that number system. Since there are 10 symbols in decimal number system, its base is 10. Each of these symbol or combination of symbols represents a numeric value. Decimal system is a positional system, and each number is represented in the powers of its base. For example, in the number 528, 8 is at unit position and represented by the symbol multiplied by base of the system raised to power 0. 2 is at 10th position and represented by the symbol multiplied by the base of the system raised to power 1. 5 is at 100th position and represented by the symbol multiplied by the base of the system raised to power 2. Decimal number is represented like this. Here 10 is the base of decimal number. The second number system is binary number system. Although this is not commonly used by humans, this is the only number system used by computers. It has two symbols. These are 0 and 1. Combination of these symbols can represent numeric and alphanumeric data. Encoding systems like ASCII, IPSYDIC, ANSI, and Unicode are used to represent numeric and alphanumeric data in binary number format. This table shows some symbols and their ASCII equivalents. Third number system in our discussion is octal number system. As its name implies, it has 8 symbols. These are 0, 1, 2, 3, 4, 5, 6, and 7. An octal number comprises of only these symbols. Here is a valid octal number and invalid octal number. Octal number system is represented like this. Here 8 represents the base of octal number. Octal number system is also a positional system, and each symbol determines its value in power of 8. The octal number 735 is equal to 477 of decimal number. This table shows binary equivalents of octal numbers. This table can be referred when you are converting an octal number to its binary equivalent. The last number system in our discussion is hexadecimal number system. There are 16 symbols in this system. The symbols from 0 to 9 represent their numeric values, and the alphabets A, B, C, D, E and F represent values 10, 11, 12, 13, 14 and 15. Hexadecimal numbers can represent very large numbers. These are used to represent memory addresses. Dear learners, computers can only understand binary numbers. The numeric and alphanumeric expressions need to be converted to binary numbers before processing. The results are then converted back to required expression. It is important to understand the conversion process. This method illustrates the conversion of a decimal number to its binary, octal or hexadecimal equivalent. The 3 steps to complete this conversion are: divide decimal number by the base of desired number system. Repeat this method until quotient is less than the base. The bottom-up sequence of remainders will be the converted number. To convert the decimal fraction, multiply it with the base of required number system. Repeat this process with fractional part only until fractional part becomes 0 or up to the required precision. The results of whole number and fractional part are then added to obtain the desired number. Decimal point is placed in the same position in the required number as it is present in the decimal number. You can use place value method to convert other number systems to decimal number. The steps to perform this conversion are: multiply the symbols with their base raised to powers in ascending order from right to left. The calculation will give the result. The procedure to convert whole number to decimal number is same as discussed in converting other number system to decimal number. To convert the fractional part, divide each symbol of the fraction with the base of number system raised to power starting from 1 in ascending order from left to right. Dear learners, now we will discuss logical gates. The physical representations of logical operations are called logical gates. These are based on the results of logical operations. Different types of logical gates include or, and, not, complemented and, complemented or, exclusive or, and equivalence gate. Now let us discuss each logical gate in detail. The first logical gate in our discussion is logical OR gate. It is physical realization of logical OR operation. The physical representation of OR gate for 2 and 3 inputs is given here. Here is truth table for logical OR gate. The plus sign represents logical addition. It is important to note that the result of logical OR is 0 when all input values are 0. AND gate is physical representation of logical AND operation. It is drawn like this. It takes at least 2 input signals. This truth table represents AND operation for 3 input variables. It is important to note that the result of logical AND is true when all input variables are true. NOT gate inverts the value of input variable. The input is inverted when it is passed through the logical NOT gate. Physical representation of NOT gate is like this. If input is 0, the output is 1, and if input is 1, the output is 0. Complemented AND gate is represented by the equation A bar plus B bar. The truth table for complemented AND gate is represented like this. The input variables are complemented and logical addition is applied to get the result. The result of complemented AND gate is 0 or false only when both input variables have binary values 1 or true. The result of complemented OR gate is equal to OR gate with an inverter. It is represented by the equation A bar dot B bar. Different physical representations of complemented OR gate are shown here. The truth table for complemented OR gate is represented for two variables like this. The input variables are complemented and logical multiplication is performed to get the result. The result of complemented OR gate is 1 or true only when both input variables have binary values 0 or false. Dear learners, Boolean algebra was introduced by George Boole. The symbolic notations of Boolean algebra are analogous to electronic switches. The electronic switch represents 0 when the switch is open and 1 when the switch is closed or off. These values are represented by false and true in Boolean algebra. The expressions of Boolean algebra help to design electronic switches and gates. The electronic switches are considered operands. Not, and, or are operators. These are physically represented by logical gates. The operands take input in two states, that is, on or off. That is analogous to binary number system. The on-off state or sequence of on-off states are interpreted in binary number sequence. Dear learners, now we will discuss basic logical operations of Boolean algebra. These operations are used in conditional programming. These are discussed in the order of precedence. The first logical operation in our discussion is complement or logical negation. It is a unary operation and applied to a single operand. The complement value of 1 is 0 and complement of 0 is 1. When negation is applied on input, it negates its value. Let us see a simple example. Let A be input symbol and A bar be complement of A. If A contains 0, its complement will contain 1. The result of double complement is original value. Double complement is represented by double bar. The second logical operation is logical multiplication. AND operator is used for this operation. It is a binary operation and takes two variables. AND operation is represented by a dot. The result of logical multiplication is a logical value. This table shows two input variables and the result of logical multiplication. 4 rows show different input and their relevant output. It is important to note that if any of the input variables has a value 0, then the result will be 0 or false. The result will be 1 or true only if both the input variables are true. The third logical operation is logical addition. This truth table shows the results of logical addition. 4 rows show different input and their relevant output. It is important to note that the result of logical addition will be 0 or false if both input variables are 0. The result of logical addition will be 1 or true if any one of the input variables is true.